Welcome back to another one of my applications of differentiation videos. This will be focusing on the maximas and minimas, or maximums and minimums, or finding the extremas, whatever you want to call it. This is what we'll be finding. The maximum, which is the top part, and the minimum, which is the bottom part, which is, minimum, maximum. Anyway, so first thing we got to do is grab our function, and I have a bunch of videos before this on critical points, and the reason I did those videos before this is because you need to know critical points before you know this stuff. This pen's a bit dead. Let's grab another one. Okay, so here we have a function, and we're going to call it x to the power of 3 plus 2x to the power of 2 plus 1, and it's going to be in the domain of negative infinity and positive infinity. Okay, so the graph will just go on forever. We're not going to be focusing on endpoints at this moment. I'll explain that in the next video where we will be focusing on a proper domain. But anyway, so we'll find the critical points, and to do that we need to find critical numbers. To find critical numbers, we need to find the derivative. The derivative of this, x to the power of 3, that's 3x squared, plus 2x squared, the derivative of that is 4x, and then it's just 0. I'm writing this in because we're going to use the quadratic formula to solve it. Anyway, so if you've watched my video on critical numbers or critical points, you'll know that to find the critical numbers of this, we set the derivative. We let the derivative equal 0. Therefore we have 0 equals 3x squared plus 4x, and then we'll chuck a plus 0. Now the reason we did the quadratic formula, because if you have ax squared plus bx plus c, you can use the quadratic formula to solve for x, and a is our 3, b is our 4, and c is the 0. Quadratic formula, if you don't know, hopefully you should know, but if you don't know, it's x equals negative b plus or minus the square root of b squared minus 4ac over 2 multiplied by a. Okay, so basically we're not going to worry about these x squareds or the x's or whatever. You use this formula to find the x. We're just worried about the numbers, so we're going to be focusing on the a, the b, and the c, which is the 3, the 4, and the 0. Okay? So, negative b. b is 4, plus or minus the square root of b squared. b squared is 4, so 4 squared, minus 4 multiplied by a, which is 3, multiplied by c, which is 0, and all over 2 multiplied by a, which is 3. Okay. Hopefully you guys have done the quadratic formula before if you're watching this video, but if you haven't, you might want to learn it. So, negative 4 plus or minus, that's 4 squared minus 0, so that's just 4 squared. We have a square root of 4 squared, which means the squared will cancel out the square root, and we'll be left with a 4. And then 2 times 3 is just 6. Okay, now we have negative 4 plus or minus 4 over 6, and that's equal to x. Now we're going to put one x value will be use the positive, the plus sign, and the other x value will use the negative. So we'll have negative 4 plus 4 on 6, and the other x value will equal negative 4 minus 4 on 6. Okay, so negative 4 plus 4, that's 0, so that's 0 on 6, which is equal to 0. Therefore, our first critical number is x equals 0. 6, and over here we have x equals negative 4 minus 4, which is negative 8 on 6. That also equals negative 4 on 3. You divide both of them by 2. And I move the negative down because if a negative is on the top or the bottom, it makes the whole thing a fraction. So it makes the whole thing negative. That's what happened here. So therefore, our second critical number is x equals negative 4 on 3. Critical number is here. Okay, now we have to use these critical numbers to find critical points. And how do we find the critical points? If you watched the video you would know, but otherwise, critical points, you basically you got these from letting the derivative letting the derivative equal either 0 or undefined. So that's how you got these, using the derivative. So now we're going to sub these values back into the original function. So we'll have x equals 0. We sub that back into the original function, which is this one here. And what you'll end up with is it'll equal 1, which is a tick, because if it equals a number, or whether it's a negative, a 0, or a positive number, it's within the domain, therefore it's a critical point. If the calculator had a fit or something and it said math error, it's maybe a critical number, but it's not within the domain, it's not a critical point. Anyway, so our second x value was negative 4 on 3. We sub that into the original function, and it spits out 59 on 27, which is roughly around 2.2 or so. Okay, but it spit out a number. Therefore, that's a tick. These two are critical points. So our critical points x equals are at when x equals 0 and when x equals negative 4 on 3. Now I know this is the same as critical numbers, but sometimes you have a ton of critical numbers and they're not, all of them aren't critical points, so that's why we do this step. Now we do the first derivative test, which is basically we use these numbers here and numbers around it to judge what the shape of the graph will look like using the first derivative. So we have our x values, big table, and we have our derivative. We calculated the derivative, and that's how we got these values. So basically we're going to have our negative 4 on 3, a gap, and a 0, and then another gap, and a gap over here, which means we have these values and we're wanting to see what happens when we go in between them and on either side, just to see what that looks like, the shape, because we got these values by letting the derivative equal 0. Therefore, if we sub these back into the derivative, we'll get 0. Same with this one. Okay? And that means the derivative is, when you calculate the derivative, you're calculating the slope, the gradient. So, in this case, the shape will be flat because there'll be no gradient. There's 0 gradient. There's 0 slope. There's not one slope. There's not negative 1 slope. There's 0 slope. Okay? Anyway, so what we're doing is we're going to pick a number on just less than this value and in between these two values, and then we're going to pick a number more than this value and just see if it's, so we can see if it's going up or down, or so we can judge where this sits. So we'll pick a number. We said this was somewhere around -1, between -1 and -1.5. So, well, it's 4 on 3, which is -1.333, or whatever it is. But we'll pick -1.5 because that's more in the negative direction, which means it's on this side. We'll sub that in, and we'll get a positive number. We're not really too concerned about what number it is. We just see if it's positive or not. Because if it's positive, that means it has a positive slope, which means it goes up like that. So the first part of our graph goes up and then stops at this point. Now we'll pick a number between -4 on 3 and 0. Let's just say -1. Okay, we sub -1 in and we get to the derivative and we get a negative value. That means that it's a negative gradient. So far we've got a graph that comes up, it flattens off, it goes down, and then it flattens off. Now we're going to find out over here. So we'll pick a positive one because that's greater than 0. And we sub that into the derivative and we get a positive number. That means a positive gradient. Therefore, judging by the gradients we've got here, the graph will look something like up, flat, down, flat, up again. Okay? So this is what the general shape will look like. And because we have escape to infinity, positive infinity in the x, and negative infinity, we're going to use arrows, which mean that it goes on forever. There's no endpoints. If we had endpoints, we would actually call these mins and maximums, and I won't go into that in this video, I'll go into that next video, but when we use the domain of infinity, positive infinity and negative infinity, or negative and positive, whatever, we use these arrows, which means it escapes on forever. Okay? So we're concerned about what's going on here. So as you can see here, this is a max, and this at roughly this point and this point is a min. Because maximum means that the values on either side are lesser than the y values or the fx values are lesser on either side of this point, which means this is the highest point this has the highest value of its surrounding points, and this has the lowest value of its surrounding points, which just means it's the minimum value and there's the maximum value. Okay, so and we can also say that judging by this goes up and it goes down here, therefore it comes up. That means this is a maximum, and these two come down, therefore this is the minimum. So we say that the maximum, and because this is the only max, we call it an absolute maximum, because it's the highest maximum point that we have, and this is the absolute minimum or global minimum, because it's the across the whole graph we have, this is the lowest point where it stops. Okay, this will go down forever, but it won't stop, so we don't worry about that. This is the lowest point where it stops and comes back up. Anyway, so the maximum here is at x, which will be x equals -4 on 3. We'll do it in coordinates. And what was the 59 on 27? Is that right? 59 on 27? Yes. And the minimum is at x equals 0 and y equals 1. I've got fx there, but this is basically like a graph where you could either have fx at the top versus x, or you could have y at the top versus x. Doesn't really matter. Some people like to do their functions using y, and some people do their functions using fx. It's sort of Leibniz or Lagrangian, whatever. Okay, but so those are our maximum points here and our minimum point here. And I'll show you what the real graph looks like. And it'll make sense, because the real graph, we have, I'll do fx because we labeled the function as fx, and we have x here. 1, 2, -1, -2, 1, 2, -1, -2. So the points we were given, I'll draw the graph first. The graph looks a little like, comes up here, like that, thereabouts. Which makes sense because we said the minimum was at 0, x equals 0, and y equals 1, which is here, which is correct. This is a minimum. And we said that the maximum occurs at roughly negative 1.3 of x, which is about here, and 2.2 of y, which is, yeah, I didn't draw the graph very to scale, but that's about here. So, there's our maximum and there's our minimum. Therefore, we got it correct. Okay? And that's how you calculate the maximum and minimum within a domain of forever and negative forever and positive forever. Okay, well, I hope you learnt something. I hope this video helped, and have a good day.